Good evening, everyone. Welcome to today's problem solving section on week 6 for the course Digital VLSI Testing. So, today we will see some continuation of the self test, then we will see the test compaction, and we will solve few problems. So, first, this is one of the examples for the logic test. Where this represents the external operation. So this is the fault-free signature, and this is the response part. So we like single input signature analysis. This is for the response analysis. So this is the single input response analyzer. So that you can see M is the response that we obtain, and this signature analyzer in a fault-free response, it produces this as the response. Now, in the presence of some fault, there are some values of n which is changed. Like here, it is 1, it is 0 in the faulty m, and here instead of 1, it is faulty response is 1. So, when applied through this response analyzer, we obtain the response is 1110, which is different from this. So, this fault F1 is detected by the signature analyzer. But here, this is changed. This response is changed. No, sorry, not this one. This response has been changed. And even this response is also changed. So you can see there are multiple response changed because of this fault, but still the response obtained is 1011. So this fault is not getting detected from using this response analyzer. This is for single input. Why single input? Because we have only one input for M. Next is that this is for MISR, which is the multiple input signature register. Okay, this is not for response analyzer, this is register. Sorry for the correction, but this is actually a response analyzer. And the MISR is the multiple input signature register, where we can see here we have multiple inputs. And to model this, we have M of x, which is the effective input sequence, and E of x, which is the error polynomial, effective error polynomial. And the error polynomial can be obtained with the division method, where the remainder will be the E of x. So next is the 4-stage MISR. So if we consider in the time shifted way, we apply this M inputs, and this is the response obtained. And the aliasing probability is given by this formula. Logic based architecture. So, like we have 4 types of BIST architecture. So, no special structure to the circuit under test. Make use of the scan chains in the circuit under test. Configure the scan chains for test pattern generation and output response analysis using concurrent chunky circuitry for the design. This, if you see, we use the scan chain which is available in the design for generating the test pattern. as well as for the response analysis. So in the type 1, we have centralized and separate board level BIST, we call CSBL. So it has two LFSRs and two multiplexers to the circuit. So you can see we have one LFSR here and another LFSR here. The first LFSR acts as a pseudo random pattern generator. PRPG stands for pseudo random pattern generator. And SISR is the single input signature and register. So we have already, yes, single input signature register. Just a input. They have given the first LFSR will act as a pseudo random pattern generator, and the second one will be used for the response analysis, which is the single input signature register. So the first multiplexer will select between the input and the other one for the primary output. So you can see when we want to perform the BIST operation, we can use the multiplexer to select this pattern generator. If on the normal operation, primary input will be applied to the circuit. Similarly, whether we want to take this response to the this will be coming to the primary output. This is the input to the multiplexer. This is another input. Whether we want the output to be applied to this SISR or between the primary output. So, like whether we want to analyze the response or the normal operation will be selected by this two multiplexers. So, built-in evaluation and self-test, which is the best, like short form is the best. Use a pseudo random pattern generator and a MISR, that is multiple input signature register. And the pseudo random patterns are applied in parallel from this generator and to the primary inputs, and the MISR is used to compact the chip output response. So we get the primary inputs, we apply this response and analyze using the MISR. So during normal operation, this will be not working. The primary inputs will be applied and this will be coming to the output. The second one is the LSSD on-chip self-test. So in this additional, we have scan chains. So we have already an internal scan chains. To that we add some external scan chains. So this method we have both internal as well as the external scan chains. And comprising all the primary inputs and primary outputs is required. The external scan chain input is connected to the scan out point of the internal chain. So here, this is the external and scan chain. We have the pseudo random pattern generator and also the primary input. Similarly, output response through external scan chain applied to the single input signature register and also through the primary output. So here will be the circuit which we want to test. Self-testing using MISR and parallel SG, which we call stumps, contains a pseudo-random pattern generation and SRSG and a MISR. The scan chains are loaded in parallel from this pattern generator. The system clocks are then pulsed and the test response are scanned out to the MISR for compaction. The new test patterns are scanned in at the same time when the test response are being scanned out. So the stems we have the pseudo random pattern generators for applying the inputs and the MISR to at the output. And these are the scan chains, separate scan channels applied for the circuit under test. Now, if we have a lesser number of, like here say some n, we can have linearly phase shifters to get more number of vectors. And again, these vectors can be compacted and applied to the response analyzer. So from n we can say reduce to n by 4 and applying increasing by n by 4, and this compactor is say reducing by 4, and we have a lesser number of input outputs to be compared and more number of patterns to be applied. So the next is built-in logic block observer. Below the architecture applies the circuit that can be partitioned into independent modules or the logic blocks. So each module is assumed to have its own input and output registers, or such registers are added in a circuit. So wherever this method is applied, wherever we can partition the circuit into independent modules. So the next built-in logic block observer. So here we can have different modes of operation. So if we consider 1 1, it is the normal mode of operation. That is, if we apply 1 1, we can see that this will be off, and whatever is there in the Y will be applied to the XOR gate. So in this way, in this normal operation, we will apply Y0, Y1, Y2 to the this XOR gate or flip flop. So this is normal operation. In the similar way, scan and mixed test generation and signature analysis. This is for the self test and the reset operation. Next is the concurrent built-in logic observer. Here also in the similar way, different operation like 0 will be normal and 1 1 in the scan. So different B1 and B2 will give different operation mode. Circular self-test pattern. So all primary inputs and primary outputs are reconfigured as external scan cells. They are connected to the internal scan cells to form a circular path. During self-test, all PI and are connected as a shift register, whereas all internal scan and primary output are reconfigured to MISR. So this one, okay, we don't have a circuit. This was the summary. Okay. Circular self-test path. So if we want to select this path, can be selected by this any mode, circulate pin. So here this MISR will apply the patterns to the circuit under test, which will be taken by the MISR, and which will again be fed back into the input. So here in the test mode, based on this XYI, this is a self-test cell. Concurrent self-verification, where this pseudo-random pattern generator will get an N, which will be applied to this functional circuit, and a second copy of the circuit, duplicate circuitry, and then finally verifying, checking the circuitry. So this two-rail checker. So concluding remarks, this STUMPS is a industry widely adopted logic-based architecture, but hits the problem due to low fault coverage. Some challenges ahead is whether the C Bilbo based architecture proposed by the authors could perform as it is guaranteed 100% single circuit fault coverage. Whether pseudo exhaustive testing could become a preferred best architecture. Now, what is pseudo exhaustive testing? Pseudo exhaustive testing means if we have n inputs, applying the 2 to the power n inputs is known as the exhaustive uh, testing. For the pseudo exhaustive testing, we have already seen in the last class, like we will be dividing the circuit into logic cones. Like say this is a circuit, I will divide this into cones. And this portion I will test exhaustively. This also I will test exhaustively. So this I will test exhaustively. And again this also I will test exhaustively. So this is called pseudo-exhaustive testing. Whether this will become a preferred best technique. These are some challenges. So with this now we will start the test compression. So why we need test compression is that the test volume is high and with the more number of test patterns, test time is also high and also test pins are high. So why can we compress test data? Because there are patterns which have don't cares. And okay, so we have an AT machine. AT machines are costly and it has a limited memory in it. This applies the patterns to the circuit under test. Now, to reduce it, we will store, like we will compress the pattern and we will keep it in the memory. And to the circuit under test, we will attach one decompressor which will decompress the pattern and apply to the circuit under test. So here we are compressing it, storing it, and before applying to the circuit under test, we have to decompress it. So we can see that the number of gates are increasing and also the volume of the test data, the number of test patterns is also increasing exponentially. And now one more thing, if we have a ATE machine, say before we were having some memory, now because of this increase in the test patterns, we cannot buy a new ATE because ATEs are also costly. So if we want say M plus 100 memory, now this we cannot buy. So what we will do is we will compress this and try to store this in this memory. And at the applying to the circuit under test, we will decompress it with the decompressor logic. So this compressor and decompressor circuits we will see briefly. So test compression categories. Test stimulus compression. So we have code based, linear decompression based scheme, and broadcast scan based scheme. Test response compression. So this is with respect to the uh, input patterns, and response is with respect to the output patterns, output or the response. The test stimulus compression is the input. So if we can't make the input to be lossy, so input should be lossless. So this compression techniques are lossless compression techniques. Whereas the output can be lossy. Like if we are going to compare it, so output we can perform lossy compression. So this techniques may include lossy compression also. Next, architecture for test compression. So as we said, we have a low cost ATE. We have some memory, so we are not changing the memory. Instead, we are to accommodate higher test patterns. We are compressing and storing here. In the circuit, this is our circuit. We are decompressing it. At the output, we are using compactor to obtain the compacted response. Um, Core based designs means it's like say it's this core is a netlist. So each core we obtain from different vendors, and we integrate all the cores to form a SoC. So every core is tested independently. So the core vendor will provide a set of uh, test patterns, because the core vendor may not know with which other components it is going to operate. So they will provide a set of test patterns. After obtaining all the test patterns for the complete, like all the number of cores, the number of patterns will be very high. So as the number of core goes high, increases, the vectors also goes increases. So this exponential like test pattern, here we need to compress so that we can use this ATM machine. Now this is So test seamless compression, we said we have code based, linear decompression based, and broadcast scan based. So where the code based came, we have four methods: dictionary code, Huffman code, run length code, and Golub code. So first we will see the dictionary code. Here we will have a dictionary which is in the circuit only, not in the AT. So the tester gives the number of bits. So if it says like say 00 is the address, in the 00 there will be one pattern. So now this pattern will be selected and applied to the all the scan chains and to the circuit. And so what is the scan slice? If I have a scan chain, say this is scan chain 1. So now I have say five scan chains. 1, 2, 3, 4, 5. So this is my second scan chain, third, fourth, and fifth. So this first cell, and in this the first cell, this first scan cells represents the slice 1. And similarly we will have the next slice. So if we have the 5 scan chains, so this is the first slice, and this is the second slice, and similarly this will be the third slice, and so on. So if say we want to apply pattern 00, this will be applied to the first slice. Say 1, 0, 0, 0, 1. And next slice, say select 0, 0, 1, 0. So this is next slice. So where this pattern will be in this tester, this B bits will be like address. Say it is in the ith index. The ith index will have this content. This content will be applied here. So this is my dictionary. And dictionary is in the decompressor circuitry. So, but here the dictionary size is a factor, like bottleneck. So now in the Huffman code, so previously it was like fixed to fixed, because like every index in a dictionary, index is also a fixed number of bits, and the index will store a fixed number of bit values. So it was like 10001, which was 5. Again 3010 is again also 5 bits. So every index will have 5 bit output. But in the Huffman coding, you can see every bit the length can vary. So if this is the pattern, so what Huffman coding will do is this pattern is repeated 22 times. So it will be encoded with a lesser number of bits. Again 13 with, and if we come which is to this pattern which is repeated only once, we need more number of bits. This is for Huffman. So the number of bits the code is having, it's varying. So we call fixed to variable. So we have a tree which we can know, so that if say if we have pattern S1 which is 0 0, 0 0 represent pattern S1, and similarly S0 is 1 0. And if you want to come here, we have to traverse the complete tree. So this was fixed variable using Huffman. Now we can see that just for having four in bits, yeah, Huffman has encoded with more number of bits. So we will go for another technique which is called selective code, where we say that whether I am going to do Huffman coding or I am just going to propagate pass the bits. So if I am going to pass, I will keep 0. So okay, one more thing, and this tree has to be stored in the decompressor. So you can see this tree is little large. That's why we go for selective. So we have one where the frequency of occurrence is more, and we have performed the Huffman coding. And we have another bit. We add one bit. This bit is extra added bit, which is for this. And if it is 0, we are just giving the same actual pattern. It's an actual pattern. We are not performing any Huffman coding. So you can see when this was more number of bits, we have just passed the actual. So now the Huffman tree, I have to store only these 4 patterns. So you can see just this 3 patterns are enough. Is it 3 or 4? Sorry. 1, 2, 3. Just 3 patterns we need to store in the Huffman tree. So this is only required to be stored in the deep compressor. And the tree is also became very. This is about the selective code. Next is the code based schemes, where we have run length code, variable code. So we consider the symbol to be 1 or in this pattern. And in this pattern, we apply it through this XOR and then apply to the circuit under test. And we code this thing using a code word. So this is of variable length and this is of fixed. So variable to fixed. So in the Galop coding, what we do is that if the in the run length we have a tail part and a group part. So this complete thing we have group as 0 and we have a tail which is all combination of a 2-bit number. Similarly for A2 and other patterns, and we merge both the group and the tail pattern to obtain the code word. So here this is also run length is also variable, code word is also variable. So this is variable to variable. And so this is example for Galop coding. So if we consider, it is always considering the pattern to be looking like 001, 0001. Okay, so this kind of patterns, and with this you can see the length. Test stimulus compression. So linear compression based schemes. This is for the test stimulus. Combinational linear, the second method. Combinational linear decompressor or fixed length sequential linear decompressor, variable length sequential linear decompressor, combinational linear and non-linear decompressors. Here the linear compression based scheme, we have this circuitry which will generate the pattern. So we have x1 to x10 which is capable of generating z1 till z12 patterns. And in this way you can see how z4 is x1 xor with x6. This circuit, this is v4 which is nothing but x obtained from here. So this x1 is coming to this input, and this input is x6, which is giving the z7 in a similar way for other combination. Linear decompression based scheme is similar to like a matrix multiplication. Again, this 10 x1 to x10, we can obtain z1 to z12. So here we can use a Euclidean, Gaussian elimination, and this place wherever there is don't care, we remove it, and this patterns we are applying, and this is this value. So Euclidean elimination, we obtain this value, but when there is these two are same, we cannot use the this not Euclidean, sorry, Gaussian elimination. So there is no solution. Combinational linear decompressor. So here we use some XOR gate network and MISR for the response analysis. Fixed length sequential linear decompressor, we have LFSR circuit. So lesser number of bits coming, LFSR will have little more number of bits, and we use a combination linear expander and then apply to the different scan chains. And variable length sequential. So here we have B to M combinational linear expansion. So this bit, one bit is applied and other n minus m minus 1 bits are obtained from this LFSR. Combinational linear and non-linear decompressor specified bit tend to be highly correlated. So this is, we have a B bits coming from the tester. We apply a linear decompressor and followed by a non-linear decompressor and then apply through the scan chain. So this has highly correlated specific bits and it combines both linear and non-linear together to achieve greater compression. Another method is that if we have the circuits and needs the similar patterns, we can broadcast the patterns to the different scan chains. So we can have also to generate such similar patterns, we can force the ATPG tool, say instead of generating test pattern C1 for C2 separately, we tie both the inputs and say we generate the patterns for this circuit. So the patterns required will be same for both the circuits. So we can now broadcast the, and this is for the pipelined circuit. In the scan architecture, this is like applied to in the broadcast mode, and we obtain it parallelly and use MISR because multiple inputs are there and get the scan out. But the same thing, if we connect it sequentially, we can apply the pattern sequential mode in the serial mode and then obtain the output. So we have static and in the reconfigurable broadcast scan, reduce the number of channels. So we have both static and dynamic configuration. Static in the means that after like we can reconfigure only for a new pattern. Now for dynamic, when we are scanning it and pattern, that time itself the configuration can be changed. Broadcast scan based design. So if we consider these are the vectors, this is a set of one vector and this is another set of vector. So here we can see that vector 2, 3 and 6 can be compacted because it's a x0, x1 and 3 is x1 and what is 6, x0, x1 X. So this can be compactor. This will be the compact pattern. So this can be merged into one pattern. And similarly, so this is for the next set, this set. So next, this is the block diagram of Mux network, where it selects between different pins based on the Mux for the broadcast scheme. Okay, virtual scan, we can use multiplexer or XOR network, and no need to solve the linear equation. It is dynamic compaction, can effectively be utilized during the ATPG process. So very little or no fault coverage loss. So now it comes for the test response compaction at the response. So we can have space, time, and mixed space and time compaction. So now this is the architecture. Like we apply a pattern to the circuit under test. We get m bit wide output pattern. Now if we have a space compactor, we get p bit wide patterns. But whereas in the time, so this is like this much big. This was the m bit pattern, output pattern. Now it is compacted to p bits. So the number of bits are reduced here. Are reduced in the that wide means the number of bits are reduced for the space compactor, whereas the number of patterns are reduced in the time compactor. So you can see that we have n number of patterns. So before it was like 0 till n patterns. Now this is reduced to 0 to q patterns. So this is reduced to 0 to q patterns. So this is reducing time compactor is reducing the number of patterns, whereas the space is reducing the number of bits. So these are with various compaction schemes. So space compaction, we have zero aliasing linear compaction, X compact, X block, X masking, and X impact. For zero aliasing, this formula is important. This formula is important. So for a test set T, for a circuit that implements function C, so if we consider there is zero aliasing means the fault will be masked. Output space for C with Q outputs log 2 modulus of the test set number of test patterns plus 1 and C. For G, be a response graph. If G is Q power 2 power Q colorable, then there exists a Q output, zero aliasing space compactor for the circuit C. So here we will use something called as graph coloring method. So if we consider this to be circuit where we have this as the test set, say now this and this can be have some edge. So now how can we perform the color? So with wherever there is a net, so first I start say I give a blue color here. So wherever there is an edge, I need to use a different color. So I will use a red here. And this also has an edge. So I can't use blue, I can't use red. So I use green. But at this node, I can't use blue and green, but I can use red. So instead of 4, I have now 3. Now 3 colors are reserved. Selection. So in this way, the response is compacted. X compact is X tolerant response compaction technique. Error masking X compact matrix. So these are the two theorems. The only single scan chain produces an error, and at any scan output, the X compactor is guaranteed to produce an error at the X compactor output at that scan out cycle. If and only if no row of an X compactor contains all zeros. An error from any one, two, or odd numbers of a scan chain at the same scan out cycle are guaranteed to be produce an error at the X compactor output at the scan out cycle if every row of the X compact matrix is non-zero, distinct, and contains an odd number of 1. These three conditions are there along with this number of scan chains. Then only the output will have an error. Output of the circuit having error, and then X compactor also having error. So X compactor with 8 inputs and 5 outputs, like here we use XOR gates. So we have more number of inputs and we compress it to get the output. So you can see this compression uses SY1, and this is from SS3, SC3, and similarly this is coming from SC4. So this way we just compress it using the XOR. X compact matrix, so we multiply this M transpose into S, which gives the output. So you can see we have here 8 values, but output we will get just 5. Space compaction, X blocking. So X can be blocked before reaching the response compactor, ensures no X will be observed. So this may result in the fault coverage loss, add area overhead, and may impact delay because we are going to add a multiplexer. So in the multiplexer, if we get any X, we mask it, we block it from reaching the compactor. That is this method. So X masking can be masked right off before the response compactor. Mask data is required to indicate whether the masking should take place, and mask data can be compressed. Possible compression techniques are weighted pseudo random LFSR reseeding or run length encoding. An example of X masking circuit. So we have a mask controller, and say if there is some X, then we can mask through this controller and then obtain at the compactor. Time compaction. A time compactor uses sequential logic to compact. Why we sequential? Because it's respect to time, and only sequential logic have this memory. So MIMSR is widely used. So this is the multiple input signature register, and this is used for the time compaction. Mixed time and space compaction. So you can see because of this XOR gate, it can obtain work as an MISR. It's like I have a circuit under test, and we apply for performing a space compaction, and then followed by performing a time compaction. So this is called um, test response compaction. That is the mixed time and space compaction. So here you can see this is similar, like having an XOR gate in between will act like an MISR. So we have an XOR gate will act like an MISR. And between multiple inputs applied to an XOR, previously we have seen somewhere for the space compaction. Yeah, different XORs can act like a. See, this are this many input lines 1, 2, 3, 4, 5, 6. But we have output 1, 2, 3, 4, 5. So both space and time compaction. And in this are some these are the industry practice. So industry solution category like uses both the linear decompression based schemes with 2 steps and broadcast scan based schemes. The general scan architecture for this is like we have broadcast scan. So this is applied through this scan different scan channels, and we have an MISR and then space compactor XOR network. So with this we have completed the briefing for the briefly about the test compression and BIST. Any doubts? We will solve some questions from the previous year as well. So if no doubts, first question. Which of the following architecture uses external scan and in addition to internal scan architecture? So this we have already seen in the class that LSSD on chip. In the slide we have already mentioned that it uses the internal scan and external scan chip. So correct answer is option C. Next question. Which of the following architecture is applicable exclusively for circuits that can be partitioned into independent modules? So this also we have seen. The architecture applied to the circuit that can be partitioned into independent modules in logic block. We can use build-over method, that is built-in logic block observer. Next question. Which of the following operation mode of built-in logic block observer is known as BIST mode? So when we can apply the generate the pattern and compare the response. So this mode is called the BIST mode. This is normal scan and this is when we were able to apply that Y0 directly. The response for that 0, 0. Which of the following decompression technique exploits the high correlation between the specified bits? So if here we have seen that the specified bits tend to be highly correlated in this method. So when we were combining the linear and non-linear decompressor. So the answer is combined linear and non-linear decompression. So next question, given a test pattern 1 x x 0 0 1 x where x represent a don't care, fill the don't care in such a way that it is produces sufficient code when we use the collab based test system compression. We have seen that in the Gulab code we wanted a pattern to be 1. So this is how we wanted the patterns. So the best coding scheme like to fill these patterns will be to fill with zeros. So now what we will have 1, 1, 2, 3, 4, 0, 1, and the next one will be the 0. So this will be the And find out the configuration for the following scan chain if it undergoes reconfiguration broadcast scan. So now we have to see like which and all pattern can be compacted. So if we consider one, this and this conflicting, so we can't. This with the 3, 1 and 0, no. With 4 also, no. Then with 5, yes. So 1, 5. And 6, 1, 1, 0, yes. So 6. So this can be one pattern. And similarly, next pattern, 2 and 3 can be compacted. And the third pattern. So now we have, we can remove this. 1, 2, 3, 5 and 6. So we are left with 4 pattern, 4 only. Okay. So this is option B. Next question. For a give test set of 14 patterns, what will be the number of outputs after zero aliasing linear compaction? So we have seen in the linear compaction, this is the formula. So we noted that Q is equal to log base 2, the number of patterns plus 1. And we take the seal of that output. So now the number of patterns is 14. So 14 plus 1 is 15. We have to take log base 2 and perform the. So this we will get 3.9, which is 4. Next, in a test compaction technique, the uh, number of input pattern is 1,355 and number of output pattern is 1,250. So the number of pattern is reduced. So what we call this when the number of pattern is reduced? When the number of bits are reduced, we call space. The number of pattern is reduced, we call time. So with this, can we answer this question? So the number of patterns are reduced. When the number of patterns are reduced, we call this as time compaction. Next, it's given that the input is 42-bit, whereas the output is 37-bit. 37, 32, 37 bit. So the number of bits are also reduced. When the number of bits are reduced, we call that as base compaction. So what should be the answer? It is time and phase compaction. Error from 1 to or any odd number of scan chains at the same scan out cycle are guaranteed to produce error at X compactor output and that scan out cycle if what are the conditions? If it is non-zero, so it is correct. Distinct, and contains an odd number of ones. Contains odd number of ones, all of them. Next question. Which space compaction technique may result in fault coverage loss and may add up area overhead? So here we were, for X blocking, we were adding a multiplexer or similar circuit. So one was adding a multiplexer, so it was increasing the area overhead, and it was that it is not guaranteed, so it may result in the loss of the fault coverage. So the answer is X blocking. So any doubts still here? So any doubts till here? So if no doubts, then we will proceed with another topic. So we will discuss another topic now. So we have said that in the previous classes, when we are generating the test pattern, that time we were saying that based on the controllability and observability, we will be selecting the inputs that needs to set to a value and to where to propagate that output. Controllability and observability. But that time we didn't discuss like any metric for the controllability or observability. So how can we define how much a node in a circuit is controllable or how much which primary input is how much like observable? So to discuss this controllability and observability, as a metric, we have scope algorithm. So in the scope algorithm, uh, if we consider like if some basic gates and discuss the controllability of analysis of the basic gates. Now if we consider an AND gate, what we have to control? The inputs. So we can control this input to 0, or we can control the C is this is combinational controllability to 1, the B node, or not B node. This is A, this is B. This is combinational controllability to 0 for the B node, combinational controllability to 1 for the B node. With this, we will have this. Now, what is the combinational controllability to a value 0 for the 0. For having a 0 here, either of the one with will be should be 0. So whichever takes the minimum effort between the A or B to be 0, and we are coming to the next level, so plus 1. And similarly for 1, both should be 1, so CC1 plus combinational controllability 1 for B plus 1 for the next stage. Is this clear? I am audible, right? So what will be the combinational controllability for this OR gate in a similar way? A, B. If you have this C, now consider the combinational controllability to 0 for this C. You can unmute yourself and also answer. What will be the combinational controllability for this C node at 0? For AND gate, is it fine? Just two equation. So similarly for an OR gate, for having a 0 at the output, we want both the inputs to be 0. So combinational controllability 0 of A plus the combinational controllability 0 of B plus 1 for the next stage. And similarly, combinational controllability for 1 will be the minimum of combinational controllability of 1 for A or 1. 1 for B. Why minimum of both? Because any one is 1, the output is going to be 1, so we can control to 1. So whichever has minimum effort, we can take that, set through that path. And plus 1 for the next level. Next gate, XOR gate. So the combinational controllability 0 for this is when the output is 0, when either both the inputs are 0 or both the inputs are 1. So minimum effort, the first is combinational controllability 0 of A plus combinational controllability 0 of B, or minimum between combinational controllability 1 of A plus controllability 1 of B. Plus 1. And similarly for 1. 1, it should be like 0, 1 or 1, 0. So again, minimum of CC1A plus CC0B or CC0B A plus CC1 B. plus 1. And few more basic gates if we define a similar way the combinational controllability. For the NAND gate, CC0 of 3. So NAND output will be 0 and both are 1. So we have to set both to 0. And for 1, either of them can be 0. So similarly for NOR gate. For combinational controllability, should I have to set both the values to 1 or any one is enough? For not anyone, if it is 1, the output will be 0, right? So anyone of CC1 A or CC1 B plus 1. And controllability for 1, 0 fail plus 0 for B plus 1. Why both should be 0? Because both 0, that time only NOR output will be 1. Now for XOR NOR gate, control it to 0. It should be opposite value. So minimum of 1 for A plus 0 for B or 0 for A plus 1 for B plus 1. And for the combination controllability 1, minimum of CC0A plus CC0B or both should be 1 plus 1. Now for NOT gate, A and C, output to be 0, input should be 1. And output to be 1, input should be 0. So we have covered the combinational controllability for all the basic gates. Now we will solve one question. If we consider this is pseudo primary input and this is connected to this R and this is also some pseudo primary input. This is primary input and this is connected to this. So we consider 1, gate 2, gate 3, this is gate 4, gate 5, gate 6. And this is say Z and second this is some pseudo primary. And this is also common to be some pseudo primary. So let's just copy this circuit. Okay, no. So now, first let's levelize this circuit. So can you tell me which and all gates will be in level 1? Level 1 of the circuit. Which is getting the inputs directly from the primary input or the pseudo primary input. So this will be in level 1. This will be in level 2. What about this? It is getting from here, so it is should be in level 3. And this is also 2 plus 1, level 3. And this one, level 4. Now let's start the controllability and observability for this. To start with, this needs, okay, this needs all the primary inputs need the 1 to control it. So this will be the combination controllability if we consider this. First is for controlling to 0, next is controlling to 1. Okay. So can you tell me what will be the controllability for here at this node? I think this will be similar to this. Any answers? So what will be the controllability, the combinational controllability at this, at the output of the inverter? For inverter, we have seen it is for 0 controllability 1 plus 1 and for 1 controllability 0 plus 1. So for 0 I will take this one. This is 1. 1 plus 1 2. And for 1 0. So again 2. So now let's go to the level 3. Now what is for 0? For 0, any one 0 is fine. So 2, minimum of 2 comma 2 is 2. So 2 plus 1, 3 comma. For 1, it both should be 1. So 2 plus 1, it is 5. Before going to stage 4, is this clear? This example is taken from the Essential of Electronic Testing book. And this is important because we initially didn't mention any like metric. We said that based on if we have that two paths, like say this is one path and this is one path. If it is, say I want a 0 here, I have a minimum effort of 3 if I set any 1 to 1. There may be chance that, say, consider this is say 4 comma 4. So I will choose this path because controlling this path is easy. So this is where this controllability and observability metrics is required. And this is where we use this scope algorithm. So before going to stage 3 for gate 4 and 5, is this scope algorithm clear here for the controllability part? Any doubts? Wait for 2 minutes. If you have any doubts or you want to discuss anything, you can. So no doubts. I hope you are able to understand like why we want a metric like scope algorithm, and now we are discussing about the controllability. Similarly, we have for the observability, and this is for the sequential combinational circuit. So similarly, we have for the sequential circuit. Okay, so let's proceed for the gate 3. Stage 3 for the gate 4. So what are the inputs? 1 comma 1, 1 comma 1, and this is coming from here, which is 3 comma 5. Here it is 1 comma 1, 3 comma 5. So this is coming to the primary. Now here for an OR gate to control to 0. 0 means any one of the input should be 1. So here for 1 it is 1 1 5, which is minimum 1. So 2. For 0 all should be wait a second. For a 0 minimum we have taken. For 1 all should be 0. So for 1 all should be 0, that is 1 plus 1 plus 3 4, 4 plus 1 5. No, 1 plus 1 plus 3 is 5, 5 plus 1 is 6. And now for the AND gate. For AND gate, for having 0, either of them 1 should be 0. So 1 is the minimum, 1 plus 1 is 2. And for having controlling 1, we need both to be 1. So 5 plus 1 6, 6 plus 1 7. And this is now 2 comma 7 coming to the stage 4. This is 2 comma 6. This is an OR gate. For having 0, it should be 0 0. So 2 plus 1, it is 4 plus 1 5. And this one minimum any one effort will be this input, which is 6. 6 plus 1 is 7. So we have obtained all the combination of controllability. Now I just copy this circuit. I wanted to discuss the observability rules similarly. So maybe some 2 3 slides. So similarly, the scope observability analysis we will do for the basic gates. So if we consider uh, an AND gate C, A, B as input, how easy or difficult it is to observe this node. From output, we will go to the inputs. So to observe 1 here or an observe 0 here. So with this, we will have this was the combinational controllability. See, now combinational observability of A. This will be with respect to the observability at Z and combinational observability at B. Previously, we have seen controllability 1 and controllability 0 for this. So for this, now, how easy or difficult it is to observe the A here. To observe the A here, A value we should get at the CO of CC. To get them, what is the observability at this point? Plus, we have to control this value to a non-controlling. So, to obtain this CO of A, we should have CO of Z, and this is previously computed CC1 of B. So, similarly for B, it will be CO of Z plus now again a non-controlling value is needed at A. For an OR gate. Observe A. We have to observe the output at the output Z plus 1 for the next stage and non-controlling value is 0. For B, PU of Z plus a non-controlling value at A is needed. Now for an XOR gate, COA. Now the combinational observability of the Z and non-controlling value is both of them. So it should be either the minimum of A, the other input is B. So that combination 0 at B or 1 at B. And combinational observability at B is combinational observability at B plus the minimum to set the A at 0 or A at 0 or A at 1. So then we almost so we have discussed XOR. We will discuss an AND, NOR, XNOR, NOT, and fan-out branch. Then we will come to the circuit. So now for the NAND gate. A, B, 3 we have discussed, right? Till now. So for the NAND gate to observe A here, this node observability plus the non-controlling value which is 1 for this. Now the other value, if go for B, this should be non-controlling A plus 1 and this. Sorry. And for a NOR gate, A, B, Z, the combinational observability A, now here, okay, NOR gate. 0 is a non-controlling value, so 0 at B. And if you want to observe B, now A should be at a non-controlling value, or A should be 0. That's all. For an X NOR gate, we want either of them to be like a combination. The non-controlling value can either be 0 or 1, so whichever has the minimum input. CC0 for the other input and CC1 for the same B input plus 1. And similarly for B, it should be minimum of CC0 of A or CC1 at A plus 1. These are the observability values. Any doubts? So what will be the observability for an NOT gate? CO of A. One input, so no any controlling or non-controlling value for the other inputs. Just now, if we have a fan out branch, say this A is getting fan out to Z1, Z2, and multiple inputs, and Zn. In that way, CO of A will be the minimum of the combinational observability of this. So this also we will have in the example, so we will see. So these are all the observability for the basic gates. So with this, can we go for the example? Any doubts? Okay, so this I wanted with this one, not this circuit. So with we have. Can you explain for the XNOR again? Yes. Observability or controllability? For observability, the non-controlling value, this, okay, so for observability, if we want to say observe A, then B should be non-controlling value. For an XNOR gate, both 0 and 1 are non-controlling. If we say 0, 0, 0, 1, 1, 0, 1, output will be 1, 1, 0, 0. So you can say both 1 and 0 are like non-controlling values. Either the output will be like inverted or the same version, but both can propagate. So whatever is taking the minimum effort to control at B, either 0 or 1, is sufficient to propagate. And similarly for this, minimum either of 0 or 1. The same thing will come for the XOR also. B can be either 0 or 1, or A can be either 0 or 1. Is your doubt here? I hope your doubt is cleared. Yes, 1 will be the inverting value of the output, but what we want at the output is the faulty value 0, 1 or 1, 0. Both are fine for me. It should be D or D bar. Same for XOR also. We want the output to be either D or D bar. So here also if we control whatever is, if we have a D here, it will be observed as D bar only. It, this is fine for me, but it should not mask to 0, 0 or 1, 0. Sorry, 0, 0 or 1, 1. This is not allowed. Okay, so now we will start the observability for this circuit. So now we have to come from the output to the input. The primary outputs, the observability will be 0. No efforts. So sorry, this is in this stage. This is 0. Again, this is not. So 2, 7, 0, 5, 7, 0, and 3, 5, 0. So now let's come to this stage 3. First is the observability. Okay, so we want to calculate this observability 2, 6, 3. So this should be non-controlling value or gate. So non-controlling is 2, 2 plus 1 is 3, and 0, so 3. And now again here NOR gate. For NOR gate, non-controlling 3 plus 1, 4, 4 plus 3, 5. Because NOR gate, NOR is not observability. Yeah, it should be 0. So all the other inputs should be 0. For having 0, 3 plus 1 plus 3, 4, 4, 7, 7 plus 1, 8. 8. And here it is 1 plus 1, 2, 2 plus 3, 5, 5 plus 1, 6. And for an AND gate, non-controlling is 1, so 5, 5, and this is 0 plus 1, 6. For this, 2, this should be 0, 1, 1 plus 1, so 2. So this here, y0, it is like this, fan out branch. So one place it is 6, the other place it is 6 and 2. So it should be not 2 places, right? Only 2 places. So it should be minimum of 6, 2. So this should be 2. Not 2. Yeah, 6 to 0. So this should be 0. So we have even the fan out covered in this example. Next stage, about 2 comma 2, other input should be 0. So 2 plus 1 plus 0, 3. Again 2 plus 1 plus 0, 3. And for this primary output, it is an inverter. So 3 plus 1, 4. 3 plus 1, 4. What about this primary output? Minimum of 6 comma 6, which is 6. And for this, minimum of 8 comma 4, it's minimum of 8 comma 4, so 4. So these are the observability values. So in this example, we have covered both the controllability and observability values. Okay, so any doubts? So we have seen the scope analysis. Any doubts? So in today's class, we have seen the some portion of the BIST related to the response analyzer, because previous class we have seen related to the pattern generation. This class related to response analyzer, and next we have seen the compression techniques, and both input with respect to input and output, as well as the scope algorithm for the controllability and observability metrics. How much effort is needed to control a node or to observe a node. So any doubts? So the output what we want to propagate is that either like D or D bar. So it is like either 0, like we want to propagate the faulty response. Either fault free can be 1, faulty can be 0, or fault free can be 1 and faulty can be 0. So if we propagate through one path and we observe that the output is changed to 1 1 or 0 0, that means the fault is masked. So the non-controlling values are the values which will allow the output to be either D or D bar. So inversion is also allowed. It should not mask. So any doubts till here? If no doubts, then we can end today's session. If you have any doubts, either you can type in the chat box or you can unmute yourself. So if no doubts, I will stop the recording. Thank you all.